Hello, I'm Prateek Singh from B.Sc Honors Data Science and AI at IIT Guwahati. This is my term project video submission for trimester 7. Today, I'll walk you through my implementation of the FSRCNN architecture. Here is the roadmap for this video. I will start with the problem, then walk through tools, dataset, code, results, and wrap up with the key takeaways. High resolution images, reconstruction from low resolution inputs matters across many domains. The challenge is that powerful models like SRCNN are too slow for real time use, which is exactly the gap FSRCNN was designed to fill. I implemented everything in Python using PyTorch for its flexibility and GPU support. Training data came from the BSD 100 benchmark dataset. I also used a pre-trained VGG network for perceptual loss and deployed a web interface for live demos. I trained on BSD 100 natural images. It's a custom data loader generates paired LR and HR samples. I tested upscaling at 2, 3, and 4 times. FSR CNN uses an hourglass design, extracts features, shrinks, map, expand, then deconvolve to high resolution. Unlike SRCNN, there is no pre-interpolation step. The network handles upsampling internally via a trainable deconvolution layer. The biggest wins with the FSRCNN, it skips pre-interpolation, which alone saves a lot of compute. The hourglass structure shrinks and expands features rather than working at full resolution throughout. Now, let me switch to my screen and show the actual code. I will point out the model definition, the combined loss function, the data loader, and the evaluation loop. So these are the required libraries: Streamlit for UI, PyTorch for deep learning, NumPy and OpenCV for image processing, and PIL for importing the image or the image loading. Now the FSR CNN model definition. This is the implementation of the FSR CNN model. First part is the feature extraction where this layer extracts the features from the image using convolution and prelude activation. Second, or the mid part, is the nonlinear mapping. This section performs nonlinear mapping with multiple convolution layers. This is where most learning happens. The last part is the upscaling part. This is a transposed this is a transposed convolution layer which increases the resolution of the image. Now, the forward pass. This defines how data flows through the network step by step. Now the model weights. These are the pre-trained weights for different scaling factors. Here comes the pre-processing functions. Firstly, we convert the RGB image to the YCBCR format. We separate brightness and color CBCR. We only enhance the Y channel because it carries the most visual details. Now this converts the image back to the RGB after processing. Now let's discuss about the Streamlit app UI. Firstly, the user sets the app title, then he is allowed to select the scaling factor. Then there is an option to upload the file. After that, if the file is loaded into the model, then processing starts after the image is uploaded. We load this image and convert it into the YCBCR format. Then we normalize the Y channel. After that, we convert it into a PyTorch tensor file. Then there is a bicubic upscaling process. We first upscale using bicubic interpolation before passing it to the model. Then comes the model loading phase. When the image is loaded into the model, we use GPU if it is available, otherwise, we use the CPU. We load the train weights based on the selected scale. Then, this sets the model to the evaluation mode. After that, we run inference without gradient calculation for efficiency. In the post processing steps, we resize the output to match the original dimensions. We merge enhanced brightness with original colors. We display both the original and enhanced images for comparison. Now let me take you through the web interface of this project. So as you can see, we have to select an upscaling factor of 2, 3 or 4 times. So for this case, we are selecting the upscaling factor of 2 times, and we have given the option of uploading our image. So over here, I'm using my dataset BSD 100 to upload the image. So I'm selecting the 2 upscaling factor low resolution image, and after conversion, as you can see, our interface has provided us with the original image and also with the upscaled image of 2 times factor, and we can see the difference in quality between the original and the super resolved image. We have extracted our results, and to evaluate the results we have used these following quantities. PSNR value, which is the peak signal to noise ratio. The higher this value is, the better the reconstruction image quality is. Then the SSIM value, the structural similarity index perceptual quality score, which ranges between 0 to 1. And also the speed, the inference time that SRCNN takes in respective to the FSRCNN is slightly faster. So now let's discuss about the limitations and the future work of our project. Now, what worked out? The FSRCNN trained end to end efficiently, the perceptual loss improved the visual quality, and the web interface make the results much accessible. What are the limitations of this is that the high upscaling of 4 times degrades the quality more. The dataset diversify affects the generalization, and the training compute still is non-trivial. In future work, we can work on this project as a video super resolution converter and also use dynamic upscaling factors. Now, concluding this project, to wrap up, FSRCNN is a practical, efficient solution for single image super resolution. The project confirms its speed advantage while being honest about quality trade offs at higher scales. Thank you.